Hello students, in this video we'll see how to translate the Laplace transform. Let's first find the Laplace transform of an exponential shift of a function. To do this, we'll use the definition of the Laplace transform. So, the Laplace transform of e to the at f of t as a function of s will be the integral from 0 to infinity of e to the at f of t e to negative st dt. Now I will group the exponential terms together and see that this is the integral from 0 to infinity of f of t, then e to the t, and then I will have an s minus a with a negative sign. So I'll have a negative st, and then I will have a positive at, so this will all work out, dt. And we see that this is exactly the definition of the Laplace transform, not at the variable s, but at the variable s minus a. So from this we can conclude the Laplace transform of e to the at f of t as a function of s is the Laplace transform of the function f evaluated at s minus a. So for example, if I wanted to find the inverse Laplace transform of the function 1 over s minus 1 quantity squared plus 1, I would note that the Laplace transform of sine of t as a function of s is 1 over s squared plus 1, and that would imply that our Laplace transform will be the sine of t multiplied by e to the 1t. So our inverse Laplace transform will be e to the t sine t. Now let's see how it works when I shift a function. So let's find the Laplace transform of the piecewise defined function. It's the function that is 0 if t is less than a, and it is f of t minus a if t is bigger than or equal to a. So I'm finding the Laplace transform of a piecewise defined function which shifts the function f over by a units. So if I have a graph, here's the t-axis, here's the f of t-axis. This function, this piecewise defined function, will be 0 up to the moment of a, and then at the moment of a, it will start at f of 0 and give me the rest of the graph of f. So the Laplace transform of this function will be the integral from 0 to infinity of, well, let's think what happens. I'll have 0 before up to time a, and past time a, I will have f of t minus a. So I don't start at 0, I will rather start at t equals a, and then I will have f of t minus a e to the negative st dt. Now I will change my variables. What I will do is I will let tau be t minus a as my substitution. If I do this, d tau is dt, so this will be the integral. Now when t is equal to a, tau is equal to 0, and when t is equal to infinity, tau is equal to infinity, and then I will have f of tau, then I'll have an e to the negative s, and t will be replaced with tau plus a d tau. If I simplify this, I will see that I have a factor of e to the negative sa, e to the negative sa, which will come out of the integral. Then I'll have the integral from 0 to infinity of f of tau, e to the negative s tau d tau. And this expression over here is nothing more than the Laplace transform of the function. So this will be e to the negative sa times the Laplace transform of the function itself. To see an example of this, if I wish to find the Laplace transform of the function which is 0 when t is less than 1 and 1 when t is greater than or equal to 1, I will apply this formula with a equals 1, and I need to find the Laplace transform of 1. But the Laplace transform of 1, as we know previously, the Laplace transform of 1 is 1 over s. So the Laplace transform of this piecewise defined function will be a is equal to 1, so e to the negative s over s. So, to conclude, when I have a piecewise defined function that starts at a certain value a, that will multiply the Laplace transform by e to the negative sa. And when I multiply the function by e to the at, that will shift the Laplace transform over. This will be useful when we're solving boundary value problems and initial value problems where there's an initial shifting or a force in the initial conditions. Thank you very much.